Welcome. I'm Carl Tate. The topic here is global plate tectonics. We will present evidence of some of the key data sets used to identify tectonic plates, the relative motion between them, and their motion with respect to the deep Earth. We start with a familiar map of the world. This is showing topography. So elevations that are above sea level, with greens being closest to sea level, going into the whites, which are highest above sea level. We're looking at basically the familiar map of the continents of the world. We can look at some high topography regions, two here, one in the Himalayas caused by collision of India plate with Eurasia plate. We saw this animation earlier of how this happened over millions of year time scale. And today there are earthquakes greater than magnitude 8 that occur and associated with this tectonic process. So a process lasting millions of years, forming these great mountain ranges and colliding between two plates. Over millions of years, we're also having large earthquakes over that same time, right up to today. So we have large magnitude greater than 8 earthquakes, and these mountains continue to be formed. Another example, not as well known, is the high topography of the St. Elias Mountains, the largest coast mountains in the world in Southeast Alaska. It's caused by collision of a chunk of thick material attached to the Pacific plate called Yakutat that collides with the North America plate. And there too, we have earthquakes greater than magnitude 8. Last one, that scale, happening in 1899. But the point is, again, that the timescales of millions of years, plate tectonics forming these mountains, is the same process that gives us large earthquakes in these regions. We now look at the other end of the scale in the negatives, where we have the purple being minus 4,000 meters below sea level, 4 kilometers, and the reds being the closest to sea level, or these shallow seas. And here we see there's a lot of really cool and interesting features below the ocean surface. We don't think about this all that often, but when you see maps like this, it leads to a lot of questions about how things came to be what they are. And in the ocean, we start with that the deepest subsea regions are defined by these trenches. That's the word. You can see one here along Kamchatka, Japan, here north of New Zealand, the Tonga-Kermadec Trench. These are the deepest regions, and they're associated with subduction. In fact, the deepest point on Earth is here, the Challenger Deep, 11,000 meters below sea level. So it turns out it's plate tectonics that essentially creates these trenches, and it's the trenches that help us define these plate boundaries. We also see regions such as along here. These are the blues, would be things that are up above the deep sea. So the purples being at, say, 4,000 meters below. As you get into the blues, at, say, 3,000 meters or 2,500 or so. These are basically mountain ranges formed. So they're highest subsea regions. That's mountain chains that occur off the sea floor, and they're associated with buoyant material, where it turns out where new plate material is created, and it's buoyant and it rises above the cooler regions. Right now, we're just kind of identifying patterns in the bathymetry, but what we'll see is that this information is very important for helping to define where these plate boundaries are. We can see lines in here. They're clearly systematic features in the bathymetry that warrant some explanation, and plate tectonics provides that. We can add the coastlines to help us see the divide between plus and minus elevations. But from a geophysical perspective, the Earth is divided into continental crust, which are basically regions above sea level, as we saw here, but also these red regions. These are no different really from the rest of the continent here, except they're slightly below sea level. So this is the continent as defined give us a picture based on the bathymetry and not so much the coastlines. And so these continental crusts shown here, the boundaries between continental and oceanic crust, which are the regions of the deep sea floor, are known as continental margins. So defining the margin of the continent is, you can kind of see right here as I'm drawing, it's basically the red portions are helping define that margin. And it's not, these margins are not in general coastlines. We now look at a distribution of earthquakes on the planet. This shows all earthquakes above magnitude 5.5 since 1976. There are more than 17,000 dots on this map. That sounds like a lot, but just to say there are millions of smaller earthquakes that have occurred. It's enough to get a picture of plate tectonics and an understanding to just look at the largest ones. It's also a set of events where we have a pretty good idea that we're capturing all the magnitude 5.5 earthquakes that have occurred thanks to this distribution of stations on the planet, something we haven't discussed. So here shows the earthquakes. We really don't know exactly what we're looking at aside from the longitude and latitude, but it turns out that, you know, defining plate tectonic boundaries, as we saw in some earlier videos, we could describe it at the simplest level as connecting the dots. In other words, as you look at the plate boundaries as defined through a lot more information and data sets, we can see, well, earthquakes are a key component in that definition. We can see a lot of these boundaries have black dots on them or very nearby. And so there's an extremely good association between plate boundaries and earthquake occurrence, especially for subduction zones. If we look, this turns out to be Aleutian, Alaska, Western Pacific, but here we're kind of unbiased by just looking at plates and earthquakes, and we can see that most plate boundaries have earthquakes associated with them. Here we can throw on the continents to get a better idea. Here we are in Alaska. This is the Aleutian Alaska subduction zone. And on the Western Pacific, we have this, can't even see the plate boundary, but it's underneath all those dots. On to active volcanoes. We're looking at a database that describes active in terms of something that has erupted during the past 12,000 years, the Holocene. So here we have to remind ourselves, geologically, 12,000 years is the blink of an eye, and that's considered active, whereas, you know, when we're talking to someone else, 12,000 years ago sounds like a long time ago, but that's active for us. So this shows the map of the world. And like earthquakes, one of the important things is earthquakes don't occur just anywhere on the planet, and neither do volcanoes. They're in fairly localized regions. Again, here showing the association between the plates and the volcanoes, we can see very good agreement between the locations of the volcanoes and the plate boundaries, especially what we know to be the subduction zones, such as over here on the Western Pacific, north of New Zealand, along South America, Andes. We can see that these volcanoes arise from plate tectonics in these settings. We can also look at hotspots, and hotspots are special kinds of volcanoes. We'll talk a little bit in a few slides. The main point is that there's no real connection between these special volcanoes and where the plate boundaries are. So hotspots are special volcanoes. They don't seem to be related to plates. Many hotspots in the oceans form islands that are well known. Hawaii, Iceland, Bermuda, Galapagos, Easter Island. There are also hotspots located on continents such as Yellowstone, Wyoming. We now show how these data sets relate to each other. So if we look at just an unbiased view, here's earthquakes and volcanoes, no coastlines. We're just saying, how are they related? And we see strong correlation between earthquake locations and volcano locations at subduction plate boundaries. So you can't tell from the map what subduction, but we'll be coming back to this in various ways. And this is the Aleutian-Alaska boundary, the Western Pacific, Kamchatka, Japan. We can see New Zealand, Tonga, Kermadec in here, Western South America, the Andean margin. Very good agreement between earthquake locations and volcanoes. If we look at volcanoes and hotspots, we can think of hotspots as volcanoes. They don't all appear in the active database of volcanoes, so you don't see a black triangle inside every red one. And the reason is just sort of difference in time scale. The black ones erupted in the past 12,000 years. Not all hotspots have had a volcano that erupted that recently. So these are important, but for us, we can think of them as volcanoes. So back looking at topography and bathymetry, here are the following items expressed in topography and bathymetry. First, we have the continents and the oceans. That's kind of the obvious, most familiar one. 0 sea level gives us the difference between the continents and the oceans. But we also have, more relevant to us, is the distinction between continental crust and oceanic crust. And there, really look at the red. The red is giving us a better idea of the continental margin. To us, what the continent is not the coastlines, it's this margin, and it helps define this crust of the continent, which tends to be much thicker, say 30 kilometers or more, than oceanic crust, which can be sort of like 8 to 10 kilometers. So here we see the oceanic crust mostly in this purple regions. We also see that topography and bathymetry helps us find the plate boundaries. And I'll flash back here and forth, but this shows the plate boundaries. And we can almost see, it almost looks like there's kind of a blue highlight going around the plate boundary. That blue is this elevated mountain range caused by buoyant material where new ocean floor, new sea floor is being created, sort of hot material that is buoyant and rises up, and to make these mountain ranges underwater that are higher than the deep sea floor. So here we can see, especially the bathymetry is helping define these boundaries. And in some cases, the other one is the trenches that we mentioned. So these lines here, that is the plate boundary for subduction of one plate going under the other. And the last one is the hotspots. We can see Hawaii, we'll revisit this soon, but a lot of these dots out in the ocean that, there's some story to each of these, and we'll see that some of these are giving us an idea of points where volcanism occurs and plates move on top of them. So here are the plates of the Earth with the topography and bathymetry. Coastlines to help us ground the geography. So hotspots are volcanoes that lie at the end of a linear chain of volcanoes. Let's start by looking at Hawaii. That is the hotspot track that points from the hotspot, which is at the youngest volcano, towards the older past volcanoes. So the hotspot, sort of where volcanism is now, say Kilauea in Hawaii erupting away, it's in the news, on and off, and it points, you can point the hotspot track toward the older volcanoes, and we'll revisit this. Hot magma upwellings beneath hotspots remain fixed relative to each other while plates move at the surface. So hotspot tracks, these lines of volcanoes that we see in parts of the ocean, can be used to infer how plates move relative to the deep earth. And it helps us understand how they move relative to each other. Age of the seafloor. New seafloor is created at mid-ocean spreading ridges. And so first, let's just take in this map. It's telling us, based on information collected from rocks and magnetism in the ocean floor, it's telling us the age of the seafloor from 0 to about 180 million years of age. Red means young. Red is the places where seafloor is being created today, slowly but surely. So here we see all this red material would be plate boundaries that we can infer to be associated with spreading boundaries. And here, the Mid-Atlantic Ridge between South America and Africa, we can see another one of these red items. They give us a picture of where new material is created on Earth. Most of the seafloor is younger than 200 million years, just based on this color scale. That sounds like a long time, but by comparison, the oldest rocks on land are 4,300 million years old. So this pattern on the seafloor is really a portion of Earth's history. Here's a map showing actually the age of the continents from a published paper, and this is in millions of years. So this shows that, you know, the dark purple here is 3,000 to 3,500 million years old. That's 3 to 3.5 billion years old. And we see that there are pockets of this on pretty much all the continents. You can see these purples in here that are showing the oldest material on Earth. By comparison, the oldest seafloor would be less than 200. So sort of at the youngest ages here. So back to the seafloor, which is kind of a key piece in the history of plate tectonics. This spectacular view of the Earth's oceans evolved from the 1960s to today as people collected and analyzed rocks and materials from the seafloor and made measurements of magnetism of these materials. The pattern of seafloor age shown here, observations, warranted an explanation for how they formed, and that explanation was plate tectonics. There's so many systematic features when you look at this information that it sort of demanded a holistic view of how this happened. And that's where plate tectonics came in out of the 1960s, even though these original ideas were really put forward in 1912 by Alfred Wegener. Takeaway topics: earthquakes do not occur everywhere on Earth. They occur in focused regions that help define the boundaries of plates on Earth. This is the connect the dots idea. The interior regions of Earth's plates are mostly devoid of earthquakes and deformation. High topography is associated with earthquake-prone collision zones, such as the Himalaya, such as between the India-Eurasia plates, and the St. Elias Mountains in Alaska, between the Pacific and North America plates. High subsea topography is associated with spreading ridges where buoyant new oceanic crust is formed. The deepest parts of the ocean, trenches, are associated with subduction, earthquakes, and volcanoes. Finally, hotspots are points on Earth that form the youngest part of a linear chain of volcanoes. As we will see, these hotspots help our understanding of plate motions.